All right, now, so we just finished an experiment to help us determine the refractive index of water. All right, we did that, and we just got a rough estimate value of 1.74. If you run this experiment severally and take average value, or you go through graphical method, you would get a better result. But even when you browse it, the refractive index of water is around 1 point something. Are you getting me right? So we are not far from being correct. We're still in line. So you see, this experiment, science, and they are really live something that we can do from the comfort of what? Our home. Now, let us translate this thing to theory now. Are you ready? So get this question. The depth of a pool is 5 meters. The depth of a pool is 5 meters. First off, a fish at the bottom of the pool, a fish at the bottom of the pool appeared to be 3 meters from the surface of the pool. 3 meters from the surface of the pool. All right, so our viewers are going to try this, as we also are going to work ours. Now, this is the question. Are you there? Put full stop there. Calculate the refractive index of the water in the pool. Calculate the refractive index of the water in the pool. All right, so that's the question. Now I'm going to ask you some things so that we guide our viewers at home. I'm going to ask you a question from the data, the information given to us. What is the actual depth of the pool?
5 meters.
5 meters, that's correct. I hope you are following. 5 meters is the actual depth of the pool. Now, from the surface of the water in the pool to the point where the fish was seen, So based on the question, we assume there is a fish at the bottom of the pool, but when you view it from the top, from the surface, the depth, according to the question, is 3 meters. Is that not so? So the 3 meters, I'm going to ask you, what does it represent?
Yeah.
Which depth?
Apparent depth.
Apparent depth. I hope we get that. All right, so this is the question we are going to solve. Theoretically, we've done this thing in terms of practical, okay? Our viewers at home, as you're working on this, you too should be doing your calculation. Is that okay? I want to get a refractive index. So, please, I'm watching. So you tell us how we go about it.
Okay. Refractive index N. The formula is equals to real depth over apparent depth.
Okay.
And our real depth is 5 meters. And apparent depth is 3 meters. What you do, 5 divided by 3.
So let's get a value, 5 divided by 3, and see.
Which is equals to 1.666.
Okay.
Which can be approximated to 1.70.
Good. So do yours and check if you got what we got here, which is 1.70 approximately as the refractive index of this water that the fish was found inside. So it's a simple one, all right? We're going to see another question right away. All right, now we are set for the second question, all right? I guess we are all ready for the second question. Now, I have a pin. So, there's a pin. There's a pin. Show you. There's a pin. Okay? So, we want to demonstrate something and then we'll translate it into theoretical question. I'm going to place the pin on top of this paper, on this table. I hope you can see the paper, all right? So, I've kept the pin on top of the paper. Now, this is a rectangular glass block. Take a look. This is a rectangular glass block. You can see the slab. All right, so I'm going to place this rectangular glass block on top of the pin this way. I've placed it Now, following the experiment we just ran in determining the refractive index of water, if I look straight on top like this, okay, at 90 degrees, I'll be seeing the pin, and then the pin is lifted up. If I'm to trace the pin with the search pin, the pin is somewhere here. So you notice that's what I'm seeing. Are you following, right? Good. There is a depth from the base. It was lifted up. So we're going to use this to solve a question theoretically. We're going to use this idea. I would formulate a question and then we'll see how far we can go. Are you ready? Are we ready to do that? So let us go. A glass block is placed. A glass block is placed on a pin. If the real depth of the pin is 12.5 centimeter, and the depth of the pin from the bottom is 3.2 centimeter. 3.2 centimeter. Calculate the refractive index. Calculate the refractive index of the glass block. Calculate the refractive index of the glass block. So that's the question. We're going to see how we solve this problem. But before we go into solving this problem, let us do some analysis. Is that okay? I'm going to ask you some questions. Let's identify these depths given to us in the question. Are you ready? First depth given to us is 12.5 centimeters. Is that not so? So what depth is that?
The real depth.
The real depth. All right. The next value given to us is 3 point what?
5.
3.5. Okay, so we have 12.5, which is the real depth. We now have 3.5. Now that 3.5, based on the statement, the question said the depth of the pin from where?
The bottom.
The bottom. So what depth is that 3.5?
Apparent displacement.
Apparent displacement. Now we are required to calculate the refractive index of the glass block. So let us see how we do that. Start working on your own, all right? Start working on your own. Let's see. So as you're working, you tell us what you're doing.
Since we know the real depth is 12.5 centimeter, and the apparent displacement is 3.5 centimeter. I mean, we are asked to find the refractive index. I know the formula for refractive index is real depth over apparent depth, and here we are not given the apparent depth, so we solve for apparent depth, and apparent depth is equal to real depth minus apparent displacement, which is equals to 12.5 minus 3.5.
So let us work in that and see. 12.5 minus what?
3.5.
12.5 minus 3.5. So it gave me 9.
No. You now substitute 9 in the formula for refractive index, which is now going to give you 12.5 over 9. That's 12.5 divided by 9.
12.5 divided by 9 gave 1.38.
Which equals to 1.38, or approximately I'm written as 1.4.
So you could see the refractive index of the glass block in this case, we calculated is what?
1.4.
1.4 approximately. So did you get that? Why not try working on that? Remember a very important point he made. When you're calculating the refractive index, all right, using this real and apparent depth method, it is simply the real depth divided by what? The apparent depth. But for this question, the apparent depth was not given to us. They gave us the real depth, and now the depth, which is 3.5, given to us is from the base. So the depth of any object from the base when a refracting substance is placed on it, that depth is called the apparent displacement. The apparent displacement is related to the real depth and the apparent depth by the formula that apparent depth is equal to real depth minus apparent what? Displacement, which is what he did. You followed along when he was solving. So with that subtraction, real minus apparent displacement, you get your apparent depth. Then go straight on to the refractive index formula. Refractive index is now the real depth, which is 12.5, divided by the apparent depth we obtained, which is 9 centimeter. And of course, get 1.38 upward approximated to 1.4. So we are done with how to calculate refractive index using the apparent and real depth method. Next, we'll be taking you on Snell's law of refraction.